I'm Gabor. Today, we'll briefly go over the two most common types of solar panels, monocrystalline and polycrystalline panels, plus a few modern technologies like half-cut cells and bifacial designs. After that, we'll have a bit of history. Trust me, it's going to be exciting. First, the classics. Monocrystalline panels are made from a single pure silicon crystal. These offer the highest efficiency. By 2026, the best models are already reaching around 24% efficiency. They also perform better in low light conditions. They have a very sleek, uniform black appearance and usually provide higher voltage per cell. Polycrystalline panels are made by melting together multiple silicon crystals, and their efficiency is slightly lower. Most modern units are around 20%, and pure polycrystalline is becoming increasingly rare because it's simply weaker. They have a distinctive bluish speckled appearance and are generally cheaper. Now, let's talk about the number of cells. For residential panels, the most common are 60 full cells or 120 half-cut cells. For larger panels, 72 full cells are typical. Newer, high-performance modules often use 96, 132, or even 144 plus half-cut cells. What is half-cut cell technology? It's very simple. The cells are cut in half, which reduces resistance loss. In cases of shading, the panel performs much better, heats up less, and overall, we get higher performance and reliability. Nowadays, almost all quality panels are made in half-cut design. Now, let's talk about bifacial panels. These generate electricity from both the front and the back, meaning they also utilize light reflected from the ground or the roof. In some cases, they can generate 10% more energy from the same area. Most of the top panels in 2026 will already be bifacial. In the next few minutes, I'd like to talk with you about some important things regarding solar panels. I hope you find this useful, especially if you're currently planning to put solar panels on your roof or to expand with a battery. First, a little bit of history. The story begins in 1839 when a 19-year-old French physicist, Edmond Becquerel, was experimenting in his father's lab and discovered that light affects certain materials. Not much progress was made until 1860, when they started laying underwater cables. A British engineer noticed that selenium behaves differently during the day than at night. During the day, it conducts electricity much better. This still wasn't a solar cell because only the conductivity changed due to the light. In 1883, an American inventor coated one side of the selenium with a thin layer of gold. Its efficiency was only 1%, but by 1883, they were already able to generate electricity directly from sunlight. And now comes the part that few people know. Einstein enters the picture too. In 1905, he studied the photoelectric effect, and in 1921, he received the Nobel Prize for it. Of course, many things are associated with him, but that prize was specifically awarded to him for explaining how solar cells work. He was a genius. Around 1920, the world wasn't really interested in solar cells. Oil was cheap, power plants were already being built, and they were filled with anything they could get: oil, wood, coal, even if the efficiency was low. The U.S. Navy needed to put a satellite into orbit. That became Vanguard 1, which in 1958 was launched on March 17th. It thought that they would be the very first, but they were actually not. The Soviets had launched Sputnik 1/2 a year earlier. Fun fact, Sputnik weighed 83 kilograms and was packed with batteries, while Vanguard 1 weighed only 1.5 kilograms and ran on solar panels. Sputnik was launched by an R-7 intercontinental rocket. It took a massive 30-meter-tall launch vehicle just to successfully deliver that 83-kilogram thing into space. So we can safely say that space exploration really kick-started solar panel technology 10 years ago with polycrystalline panels and later expanded with monocrystalline modules. Thanks to the solar edge system, panels with different outputs and orientations run together smoothly. Why does this work so well? Let me talk about this for a few minutes, spiced up with my own experience. The essence of Solar Edge is simple but brilliant. A power optimizer is installed behind every single panel. They each perform MPPT, maximum power point tracking, individually. Shade, dust, different orientation, or a weaker panel never drags down the whole string. Together, they create the perfect DC voltage for the inverter. In a single-phase 230-volt household, the optimizers automatically maintain 400 volts DC on the string. That's exactly the voltage at which the single-phase inverter achieves its highest efficiency. For three-phase 400-volt systems, these same optimizers build an 800-volt DC string. Battery integration? It's perfectly seamless. In single-phase systems, a high-voltage, roughly 400-volt home battery connects directly to the DC bus. For three-phase systems, the battery has a lower voltage, around 48 volts. You can see production, consumption, battery status, and export limit. The latest 2026 models are already fully prepared for dynamic electricity contracts and energy market trading. Automatic charging during cheap periods, feeding back into the grid during expensive periods. For me, this is a zero headache category. It's completely reliable, and even in hindsight, I'm really glad I chose this. This is a small DC-DC converter that individually maximizes the performance of each panel. It has fire protection, shuts off if it overheats, handles short circuits, and as long as it's not connected to the inverter, it only outputs 1 volt. It's safe, but of course, don't go licking the DC cable. With SolarEdge, you get a detailed report. This and that panel are underperforming. Another advantage, the same string works even on roof sections with different orientations. A panel in the shade doesn't drag the others down. Everyone runs at maximum. This little electronic box ensures that the given panel delivers its maximum. They're usually screwed onto the aluminum rail, and the latter is connected with a green-yellow grounding cable. Here you can see the standard MC4 connectors. At the back, there's a small black junction box from which the cables go straight into the optimizer, and from there they continue in series. The mounting is done with an aluminum rail and a stainless steel support structure. You can see that the gap between the tiles is minimal, but where the bracket was installed, it opens up a little. They could have sanded it down a bit underneath, but it was left like this. Tip: if you're installing solar panels, make sure to use only stainless materials, not just surface-treated screws. In 15 years, the coating will wear off, the screw will rust through, and in strong winds, the panel could fall off. It's not worth saving money here. That's all for today. Thank you so much for joining me today. If you liked it, give the video a like. Thank you so very much for everything. Have a wonderful day. Goodbye.